welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel where we talk about everything I want to, science and math. And today this is chemistry class and we are talking about heat. So these are the notes. Normally I do this first period, but the board wasn't working. So y'all are going to have the notes videotaped instead. Even though, well, Cameron can watch the notes. All right, let's do this quickly so y'all can do the lab. So heat. Which one do you think has more heat? David? Which one do you think has more heat? A teacup of boiling water or Lake Allatoona at 60 degrees Fahrenheit?
Lake Allatoona at 60 degrees Fahrenheit.
It's Lake Allatoona.
Because it has all those hot fish in them.
No, it's because heat is not temperature. The teacup of boiling water has a higher temperature, but the heat includes all the energy that is stored in that. And if you imagine that, say you could somehow turn them both into a bomb, Lake Allatoona would have a lot more mass. It would be a bigger bomb. Yes?
Wait, if they're both at 60 degrees Fahrenheit, would it be the same?
Nope. It would still be Lake Allatoona because there's more molecules. Therefore, there are more chemical bonds and energy is stored in those chemical bonds. Remember we learned about that it takes energy to make or break bonds, and that energy is the heat. It's the total energy that's in it. Any questions about that? Okay, so heat is the total amount of energy that can be transferred from high to low temperatures. And the unit is called joules. It sounds like a diamond or something, but it's spelt different, joules. So cold doesn't exist. Cold is just a lack of heat. So, but heat flows from an area of higher heat to lower heat. Heat flows, the energy will flow from a higher temperature to a lower temperature place. So when my hands are cold, if I go touch the lava lamp over there that's hot, then the heat will flow out of the lava lamp into my cold hands. That's why I like that lava lamp over there. I'm always cold. Okay, so what is temperature then? Temperature and heat are not the same thing. Temperature is the average kinetic energy. Do you remember this word from physical science?
Yes.
And digging is energy. It's the average kinetic energy. And in science class, it's measured in degrees Celsius or Kelvin. And Kelvin doesn't have any degrees. It's just Kelvin. Too cool for degrees. But in English, we do Fahrenheit degrees. So that's what you normally think of. Okay, and so another aspect of this is phase change. What is a phase? Do y'all remember from physical science?
Water?
Water is not a phase, but it can be in phases. What are the phases of water? Liquid, solid, and gas. Water is steam and stuff like that.
That was stupid.
It takes energy to go through phase change. Okay, so you have to add energy to get it to go from solid to liquid to gas.
What type of energy do you need to turn water to ice?
You need to take energy away. You remove energy, negative energy. All right, I'm going to see if I can roll this over here. I'm feeling very hopeful about this new way of doing it. We'll see. Oh, look at that rolling. This is so exciting. What I did is instead of going straight with a Word document, I went PDF to Word, and it seems to be working better. It seems to help it stick together. All right, shh. Y'all are so chattery today. All right, so this is a phase change diagram. And on the test, you'll have to label it. It's got temperature on this side, energy on that side. And this, so if this is water, water is a solid, it's ice below 0 degrees Celsius, right? At 0 degrees, this is where you have melting. Then where it's liquid, it stays a liquid all the way to what temperature? When does water become steam? Where does water boil?
80 degrees?
100 in Celsius, this is Celsius, Fahrenheit, it's 212, and it's 32. So this is Celsius. So at 100 degrees, you have boiling. It boils. And that would be liquid water, and this would be steam. Now, where these things happen, where melting and boiling occur, even if you increase the energy, it does not increase the temperature. So water, ice water, where it's in between solid and liquid, is always 0 degrees. You can put more ice in, doesn't matter, it's still going to be 0 degrees. Boiling water is always 100. You can turn up the temperature and make it boil faster. It will not increase the temperature. If you will increase the temperature of the stove. It will not increase the temperature of the water. Boiling water is always 100 degrees, pretty much. We'll talk about the effect of pressure when you get to physics. So what happens here is all the extra energy is going to breaking that crystal lattice and freeing the ice from its crystal lattice so it's free to zip around as water. Once it gets to be boiling, all of the energy goes, instead of to increasing the heat, to increasing the temperature, it goes to freeing the water from the liquid, the intermolecular forces, so it becomes steam. So temperature doesn't change. It doesn't change while phase change is happening. This, where you add heat and the temperature doesn't change, is called latent heat. And you need to be able to identify where latent heat is on this diagram for your test. Change the color here. When temperature does change, when it's not in phase change, it's called sensible heat. So sensible heat is here, and there, and there. Sensible, so the word latent means hidden. Do y'all know that word from English? Latent is hidden. So this is like hidden heat. You're adding heat to it, but it doesn't change the temperature because it's going through phase change.
So sensible heat does change it.
Mm-hmm. Sensible heat changes the temperature. Latent does not. Okay, you feel pretty good about that?
That's so simple.
Can you label all that? I think this whole thing's simple. I think this is much easier than what we've been doing. And you already know this. What's the word that we learned that means a reaction takes in energy? Endothermic. See? You already know stuff.
Because you taught us so well.
Oh, thank you.
Oh, Ms. Blackburn, did you grade those tests we took before break?
I have graded the Scantron part. I haven't graded the math part. So, Scantron part was okay. Okay, and then what is it called when it gives off energy? Exothermic. Okay. Now, melting and boiling occur at specific temperatures for different substances, and we see that in our chart also. And for water, we can go ahead and fill out. Let me scroll up. Oh no, look, it's messing up. Boo. So sad. All right, I'm going to mark it out.
I think everybody has it. You can just leave it.
Okay, we're going to go back over to Word. We'll open the other classes one for a second. I don't know what we want first.
Yeah.
That one right there.
Probably. Gold used to kill in like the 1800s, so.
All right. Let's see if we can do it on this one. Okay, so what temperature does water melt at? Does ice melt at?
100 degrees.
No, melt. 0 degrees what? 0 degrees Celsius. And what does it boil at?
100.
100 degrees Celsius. Now, in Fahrenheit, what temperature does ice melt at? 32. 32 degrees Fahrenheit. And what does it boil at in Fahrenheit? 212. Very good. 212 degrees Fahrenheit. Now, what is subliming? Does anybody know that word already? Sublime?
Is that like good or something?
It does. It is a thing, word for almost like heavenly. It's sort of like sublime. Sort of has like angelic sort of connotations. But there's another word for it, meaning for it in science, and it's when something goes straight from a solid to a gas without being a liquid first. You see this with dry ice. Anybody ever seen dry ice? It's ice. It's frozen carbon dioxide, and then it gives off smoke. It doesn't melt. Have anybody ever seen that? Maybe we'll get time to look at it when we do gas laws.
I thought dry ice was a solid in the gas.
It's a solid, no, it's a solid or a gas. Well, water can actually do this. A long time ago, when I was in middle school, I hated middle school. Griffin Middle School, Cobb County. Hated it. High school was way better. Well, one time it snowed really big on Saturday. It was like that deep. It was everywhere, all over the roads. I knew that we were not going to have school on Monday because I looked at the weather and it wasn't getting up to freezing. It was going to be below freezing all the way the whole next week. Monday morning, woke up, no snow anywhere. It never got up to freezing. It never melted, but the air was really, really dry, and the water molecules went straight from ice into the air. It was so disappointing, just tragic. So what temperature does subliming happen? It depends. It depends on the pressure, and it also depends on the dryness of the air. If the air's real dry, it's almost like it sucks the water molecules straight from the ice into the air. So tragic having to go to school that day. All right, so the next concept is called specific heat. Specific heat. And it's a physical property of a substance. You look it up in tables. If you had a chemistry book, it would be in a table in the back of the chemistry book for you to look up. It might have some specific heats on the back of that periodic table that I have laminated. I'll let y'all use. But you look it up in tables. It's a physical property of a substance, just like color and melting point. And it's the amount of energy needed to change the temperature of 1 gram of substance 1 degree Celsius. And the symbol for specific heat is lowercase c. I don't know why, because specific starts with an S, not a C, but that's what it is. So you already know about this because you've lived your life and you've noticed things. And so like you've noticed that some things heat up faster and some things cool off faster. You wouldn't make an oven mitt out of aluminum foil. You'd get burned, wouldn't you? Because it would not be a good thing. It heats up very fast. But also, if you had a piece of aluminum foil that's, say, in the oven, and you take it out because you put a piece of pizza on it to heat it up, and you take it out and you sit on the countertop, you pretty much immediately can touch it and not get burned. Have you noticed that? The aluminum foil doesn't hold heat. It heats up very quickly, but it very quickly cools off. The reason why is because it has a low specific heat. If you had a pan on the stove and you started heating it up, but then you changed your mind and turned it off, very quickly you can touch that pan and not get burned. But if you had a pot and you heated it up to boiling full of water and you changed your mind and turned it off, you could not immediately put your hand in that water, could you? It'd take a long time for that water to cool off where you could put your hand in it. And it's because water has a very high specific heat. It has to do with the polarity of the molecules. Okay, everybody, cross your fingers. We're going to try to scroll up the notes. We'll see. It's not going to do it. Irritating notes. So what I'm going to do, I'm going to save the copy. Let me do it. It's too freaked out to do it. Let me do it. Boo. Let's try to open it again. Some more phone sound effects. All right, well, at least I got rid of the words. Okay. So which cools off first, water or aluminum? Aluminum. So you can circle that. aluminum. Okay, and this is because water has a high specific heat, and aluminum has a low specific heat. Why water is shaped like Mickey Mouse? Let me get on the right page here. Not hard to read. Ooh. And it's polar. Okay, so there's our little thing. Because water has a positive and a negative end, it's a sticky molecule. It sticks to itself really hard, which makes it doesn't want to change. It's sort of like water has inertia, and it doesn't want to change. It wants to stay how it is.
Isn't
Okay?
that a physics thing, inertia?
Yes, it's a physics term. You'll learn more about it. So another thing you need to know is another word for heat is enthalpy. Enthalpy is heat. And there's a formula. It's the change of heat formula. And I think it's kind of easy because it looks like it's MC delta T, but that delta kind of looks like an A. So it looks like it says cat. So this is our one formula for this unit. Very easy. I will give you 4 or of the 5 things or 3 of the 4 things. That'll make sense in a second. And you solve for the other one. One little formula, one little math problem. So easy. So like I gave you a lot of worksheets, but it's not really hard. It's just that same problem over and over again. Just to get you used to the units and some of that stuff. Okay, so sometimes you see the change of heat as an H in newer books. But in old books, usually it is a Q. Sometimes it is a uppercase Q. Sometimes it's a lowercase q. But know that Q also means heat. Okay, so Q also stands for heat. So M is the mass in grams. C is the specific heat. For water, it's 4.180 or 1 calorie, and you need to memorize that or write it on your cheat sheet periodic table. It'll be something you need to know. T is the temperature in Celsius. I'm going to just put temp. And delta is change or difference. So what are we going to do if it's change or difference? Are we going to add, subtract, multiply, or divide? We're going to subtract the temperatures. Change or difference. So we're going to need to subtract the temperatures. And we also need to use, that's not an 11. What symbol is that in math?
G.
Nope. Another one. It's a mathematical thing to do. Absolute value. And I can show you how to do that. I can show you how to do that on your TI-84 calculators. How to do absolute value also. 82, 83s. I can show you how to make those do it. All right, how are we so far? All pretty easy, right? So here's an example problem. When you read through, remember what makes a word problem hard? The words. So we're going to annotate the problem, and then we're going to get rid of the words. You drink 1,000 grams of ice. Is that a mass, a specific heat, a temperature, or a change? It's a mass. I'm going to write a little M over that. Of ice water, now water is a chemical, so that might be important. At 0 degrees Celsius, this is T sub 1, the first temperature. It warms up inside of you to 37 degrees. That's temperature 2. You write 1 and 2 as subscripts, not superscripts. What is the change of heat? So this is what I don't know, so I write H equals question mark. Now I've got everything that's important there, and I'm ready to do the problem. Now, when I do the problem, I write the formula every time. That'll help you learn it. And then I substitute it in. So right underneath M, I write 1,000. Right underneath C, I put 4.180. And right under triangle T, I put 37 because 37 minus 0 is 37.
Wait, what does the M stand for again?
Mass, the 1,000 grams.
And the C?
Specific heat, the 4.18.
Oh, yeah.
Because it's water.
That makes sense.
And a lot of them will be water. Because whenever you're doing food and stuff, it's always usually water you use. Okay, I'm going to try roll up.
What if you tried clicking out of drawer and then
That's an idea. That didn't work. We'll go back. Try home. Didn't work. Didn't work. Okay. All right, so try it on your calculator and see if you get the right answer. It is, oops, wrong place, 154,600.
You multiply it, right?
You multiply it.
and where's
We already did our subtracting, 37 minus 0.
so where's the absolute value coming?
It's absolute value is that when you subtract your temperatures, it can give you a negative number. And when you multiply negative numbers, it would be negative, but your heat should be positive. So it's the absolute value.
I got 660.
Yeah.
Well, I guess because it's rounded off, because of sig figs. Kind of.
So we put 600.
Yes. 154,600. Okay, now how do we measure directly how much heat comes in and out of a chemical reaction? It is an instrument called a calorimeter. It looks like a calorie meter,
Wait, is,
but you
this,
say it calorimeter.
is it 154.600?
Nope, 154,600.
Okay.
Okay, so these are fancy ones here and here, but this is the one we'll use at the end. It's the styrofoam cup. So we're probably going to be doing a lab maybe Thursday or Friday with this. We'll see. I have to figure out what we're doing because of the EOC. All right, any questions about that? We have the cheap one, the styrofoam cup. Okay, let's see if it scrolls. Will it scroll? Sometimes you click it a bunch, it works. Aha! So good. We'll leave that picture there. Okay, so what about units? Heat can be measured in calories. You've heard of those before. Or in joules. And it sounds like diamonds and rubies, but it's spelled different. Joules. 1 calorie is 4.184 joules, so that's our conversion factor. But there's the thing about it. The calories you've heard about are not physics calories. A food calorie is written with a capital C, equals 1,000 science calories with a lowercase c. So like your Snickers bar that says it's 240 calories is 240,000 physics calories. But the food industry didn't want to write that on your Snicker bar. They thought that might make you not want to eat it. So they changed it and divided it by 1,000. Spilling my water. Okay. So the next idea is entropy. And entropy is designated by a capital S. I don't know why it's an S, but it is. And it's delta S, a change in it. And it is a measure of the degree of disorder of a system. Disorder. It's a law. It's called the law of entropy, or it is called the second law of thermodynamics, but it's a law. So this is what it is. Entropy always goes from more order to less order unless acted upon by an outside force. That's the law of entropy. Things go from order to disorder on their own. For it to go from disorder to order, it takes an orderer. It takes someone to go and put it in order. For example, your room. Does your room ever clean itself? No. No matter if you sing It's a Spoonful of Sugar, even if Mary Poppins herself were there, the room would not clean itself unless it was acted upon by an outside force. Does that make sense? That is entropy. So like even if I had a bottle of perfume and I opened it, the molecules would be kind of orderly in the bottle of perfume, but then as they spread across, got out of the perfume bottle and started spreading through the room, they become more disordered. And is there any getting those smelly molecules back in the bottle without a whole lot of force and figuring out some science? Is there any way on their own the perfume molecules are going back in the bottle of perfume? No. So that's entropy. I always think of this. Okay, so I'm from around here. I went to Campbell High School in Smyrna, grew up in Smyrna, and so I have grown up going to Six Flags. And when Six Flags was new, they tried harder to compete with Disney and tried to have Imagineering. So the Dahlonega Mine Train, if you've been to Six Flags, you know what that is, was Imagineered to be like the first gold rush in Georgia that was in Dahlonega, and that's why like you go through that little bridge and then go down the hill like into the mine kind of thing. And they used to have this covered wagon in the middle part where it kind of loops around. If you've ridden this, okay, there was this covered wagon when I was a little kid. Imagineered barrels, things that look like gold, this lovely little covered wagon. Over the years though, Six Flags didn't bother to do anything with that, and they just let it sit there. And just over the decades, the top got torn off, then the wheels collapsed, and then it was the box part. Well, now all the wood is rotten, and when I was there for Fright Fest, just, in October, you can still see the metal chassis, and that's it. No one at Six Flags thinks, this is a little messy, maybe we should go get it. No one tore that up. It just went, because of the law of entropy, it went from order to disorder, and it was not acted upon by an outside force. Now, at Disney, they'd be acting on that, wouldn't they? They'd be painting it and cleaning it and keeping it up and selling little pins of it for you to buy in the gift shop when you got out. Not Six Flags, no. Okay, so now, let's think about it for a second. While we're talking about this, I said it's a law. And in rock, paper, scissors of science, which wins? Law or theory? Law. Law always wins. Laws are so true, they're math. They either have a mathematical equation, which entropy does, which you will learn in physics, or they have a constant, a number like gravity has a constant that goes with it. Okay, everybody got that in your head? There are two controversial theories that violate the law of entropy. What are they?
Wait, say it again?
There are two controversial theories that violate the law of entropy. What are they? What are the two controversial theories? Y'all know.
We probably do know, but we don't know which one.
What?
Collision theory.
Collision. That's not very controversial. It is a theory, though. Big Bang and has to do with religion, but it's not Big Bang.
Oh, God's creation?
No, it's evolution, and it would be people who would oppose it. Okay, so think about this. Big Bang, in case you don't know what it is the theory that all the matter in the universe started off the size of a softball. It exploded, and out of it came all the planets and stars and you and everything else. Do you see how that violates the law of entropy? Because you had disorder, an explosion, and out of it came order, you. Do you see the problem there? And the law of entropy is you do not move from disorder to order unless acted upon by an outside force. It would be like there being an explosion in a gold mine and Rolex watches come flying out. Would that happen?
Yes.
No. And you are way more complex than a Rolex watch. We know how a Rolex watch works. We don't know how you work. We don't understand all the chemistry about you. We don't understand all the science of you. And we certainly don't understand how to make life. A Rolex watch is not alive. You're alive. You can live and die. So do you understand the issues here? Now, what it means is we don't know everything, do we? I think a lot of kids, students get the idea that science knows all. Science should control all. But we don't know all. So that, and then evolution's idea is that like on Earth, that there would have been primordial muck and lightning and biomolecules, and those biomolecules would have assembled themselves into bigger molecules, which would have assembled themselves into cells, and then those cells would have grown more and more complex and gone from single cell to multi-cell to little organisms to you. Do you see how that is moving from disorder to order without being acted upon by an outside force? And it violates the law of entropy. It's also called the second law of thermodynamics. So I just always think it's a good place for me to insert the idea. We don't know everything. Don't get the idea we do, because we don't.
So there's like no clues on how the Big Bang happened.
No, and not only that, Big Bang doesn't start with nothing. Do you understand that?
Hydrogen and lithium or something?
It starts with a handful of molecules, and from it everything came. Where did those molecules come from? The thing is it doesn't start with nothing. According to the law of conservation, matter and energy can neither be created or destroyed. They can only change from one form to another. Where did the baseball come from? It starts with the baseball. They cheat. They start with the baseball. You see that? So there's still stuff to learn. You be a scientist, grow up, figure it all out for us. Okay, enthalpy and entropy. Enthalpy is heat. Entropy is this huge idea of things moving from order to disorder. This is what drives chemistry. This is the bottom line. Let me get in the right place here. Enthalpy. Okay, so this is what causes chemical reactions. That's why we're talking about this. These two ideas is what makes chemical reactions happen. And there was a scientist, famous scientist, and you will learn more about this in college chemistry or AP, who figured out when you look at the energy of a chemical reaction, it doesn't matter if the chemical reaction happens all at once or in steps, the energy is the same. The energy changes are the same. You can kind of think about it like this. Say you burn a log in the fireplace and turn that log into smoke and ash and fire. And you burn it and it takes all night to do it. Or you put it in something and blow it up. You know, like those things that they blow up suspicious packages, the robot comes out in the bomb squad and they put a little dome over it and it goes ka-chunk and it's gone. Well, it wouldn't matter if you burnt your log slowly all night or if you put it in one of those bomb things and just blew it up all at once. The energy would be the same, whether it's in steps or all at once. That's Hess's law. And you'll work a lot more on the math of this in those other classes. We don't have time. I know it breaks your heart. You want to do some Hess's law problems, you're just going to have to wait till college or AP Chem. Okay, another thing about energy. If a reaction is reversed, the sign of heat is also reversed. This has to do with how we were talking about reversible reactions and equilibrium last chapter. If you reverse a chemical reaction, the heat also is reversed. So if it's negative, it will be positive. If it's positive, it will be negative. So here's an example problem. Diamonds and graphite are allotropes. Allotropes is just a fancy science word, meaning it's that should say M, the same chemical, carbon, but they're just in different forms. They have different bonds.
Is there not a symbol in chemistry for different?
No? And then we got our little chain symbol. We need a different one. So they're different forms. The difference is graphite, the pencil lead you have, has all of its chemical bonds in one plane, like sheets of paper. Diamonds also have chemical bonds going up and down, connecting them, and that's where you get those facets and the strength, and it's not slippery, and it's totally different, right? Those are called allotropes. Now I have our lab where we can do allotropes of sulfur. It smells really bad, like rotten eggs, but I don't know if we're going to have time. But if we do, we'll see different forms of that. So you can burn a diamond. Remember in the video we saw, Adam's Ring of Truth, and Julia Child burnt the diamond in the vacuum oven. Remember that? And you can turn it into graphite. So here's our problem. You have to add energy to graphite to make it into diamond, or the other way around. How much? The enthalpies of graphite are negative 394 kilojoules per mole, and diamond is negative 396 kilojoules per mole. So let's scroll up. Let's see if we can do it. Feeling very optimistic. I didn't get the last time when I did a lot of clicking. Click, 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 click. Oh, the clicking is working again. All right, so this is what you do. There's our reaction. Graphite plus oxygen makes CO2, and then the CO2 can become diamond and oxygen. So here is the heat from the first one. That's the heat of the second one. You subtract, and these are negatives, and remember, two negatives make a positive. So it's negative plus, and the difference is 2 kilojoules. But you would just put that in your calculator. Okay, so thermodynamics. And this is the law of conservation of energy. So the first law of conservation, first law of thermodynamics is conservation, which is matter and energy can neither be created or destroyed, only change from one form to another. Ever since creation, whatever that was, Big Bang or whatever, but Big Bang, it'd have to be before the Big Bang because Big Bang starts with matter. But ever since that point, you can't make or destroy matter and energy, only change from one form to another. And that's the first law of thermodynamics. The second law of thermodynamics is things move from order to disorder unless acted upon by an outside force, or enthalpy. So the bottom line for the first law of thermodynamics is the energy of the universe is constant. Energy is not increasing or decreasing, it's just changing forms. All right, that's easier, isn't it? This is the easiest thing we've done yet, don't you think? Okay, like, share, subscribe.